Hi everyone and welcome back to PrepFusion. So today will be the last video of our electromagnetics field subject. So I hope you have enjoyed this subject. So we'll talk about more at the end. But obviously before ending, this is the last topic that we'll discuss. We'll discuss today about the self and mutual inductance. We'll discuss about the inductors as well. Okay. So before starting, obviously I gave you a few homeworks so that I will go through over those and then I will start today's topics. So this one was the homework, and I told you that what if here instead of it rotating not this one, sorry, this one was not the question, this one, not this one as well. Which question was it? I forgot. Where was it? Here, yeah. Instead of it being 90, what if it was 180? So if I just, this is the part 1, I gave you a part 2. Part 2 was if my theta was 180. If your theta was 180, obviously initial flux is b pi b r square. This is my phi initial, that will not change obviously. But finally what is happening, if you observe, finally what is happening is like initially my area vector was along the direction of the magnetic field. If I rotate a whole 180, my area vector will be pointing outwards and magnetic field direction will be this. So now the area vector is in the opposite direction. So what is the change in flux? If I do phi final will be what? It will be b dot a. It will be magnitude of b, magnitude of a cos of 180. Okay. So this will be equals to phi of f will be equals to magnitude of b is b itself, and a is pi r square, but as it is cos 180, it will be something negative. Okay, it will be negative basically. Minus 1. So now what is my delta q? I know delta q is phi initial minus of phi final divided by r. I am not recommending you to remember any formula. I am just telling you to derive all this, okay, in the examination hall itself. So this will be equals to 2 minus, no, not minus, this will be 2 b pi r square divided by the radians r. So your total charge will be this now. It will be twice the b r square, so it will be option D. Okay. So for this second one, option D will be the correct answer. Okay. This is just the modified version of the question. So let's do this question. Okay, I will just go here. This page is anyways empty. I will just remove this page. Okay, this was the question that I gave you. Here again the same thing, the velocity vector is here, angle with respect to the shortest length is theta, right? And like the theta is 53. So what will be basically your induced EMF across the ends of the wire? Like just simple formula based, what you have to do, use V induced is BLV sin theta. So it is B, and what is the shortest length? Like it will be LV sin theta. L is this length, right? Shortest length is 2r. So it will be 2r into velocity. Velocity is, have they given us the velocity? V into sin 53.13. So it will be simply sin 53.13 will be 4 by 5. So it will be 4 by 5. So it is 0.8 into 2, 1.6 b PR. So as it is 2r because the length is 2. So yeah, this answer will be simply 1.6 BVR. Okay. So yeah, I hope you have solved this question at the homework. So now we'll start with today's topics. So today's topics, first of all, we'll understand what is inductance. Okay, what is self-inductance? So self-inductance is a property of a coil that causes it to oppose any change in the current flowing through it by inducing an EMF within itself. So this language is a bit typical, but actually what inductance is, the property of a coil to generate magnetic field. Just like capacitor, right? The property of the capacitor was what? To store charges. The property of inductor is to generate magnetic field. The property of capacitor was to store charges, and that was known as capacitance. Okay, and here it is known as inductance. That's it. That's simply it. So there is a one device that can store charges. There has to be another device that can generate magnetic field. The capacitor used to generate electric field between its plate, right? Here inductor generates magnetic field between its plate. Yeah, sorry, some important call came up. As I was telling, it is the property of inductor to, like, what is the property of inductor? It is inductance, and it is the ability to basically generate magnetic field. So, and how does it generate magnetic field? What it does, it opposes the change that is current is flowing through it. It opposes the change. If some current is flowing in this direction, it will say no, I don't want the current to flow in this direction. I want to be at steady state. Okay, I hope you know that inductor and capacitor both oppose the change in energy. They want to stay in the same state. Okay, that comes from the Lenz's law. Okay, so basically what happens in inductor, if the current through a coil changes, it causes a change in magnetic flux, and as it causes a change in magnetic flux, as magnetic flux changes, it induces an EMF, and that phenomena is known as self-induction. As due to its own magnetic flux, it is generating an EMF. So that's why self name comes into the picture. That's why self-induction. Okay, so I have a current I, due to which a magnetic field gets generated, and if the current is changing, there is a di, and as the current is changing, there will be a dB, and due to that dB, what will happen? There will be a d phi, and due to the d phi on the coil itself, as the flux is cutting the coil, what will happen? A voltage V induced will be generated, and it will be such that it will oppose the change in current. So it will oppose this. Okay, because I don't want to change my state, I want to remain in the same state. So that's why this is also sometimes known as self-induced EMF, and the property of this particular thing is known as self-inductance. I hope you understood this one. Because it's due to its own change in current, it is inducing some EMF. So there is, like, the formula for inductance. Self-inductance is psi is the flux equals to Li. So the relationship between flux and current, it is related with the inductance. So psi is equals to Li, and L is known as the self-inductance, or the self-inductance of the coil, or the total flux through the coil per unit current. Okay, for total flux through the coil per unit current, right? Per unit current. If I divide both sides by I, it will be flux per unit current, and that is the basically units of it. Its unit is Weber per ampere or Henry. Now remember this is a very important unit, and if you have studied electrical engineering, I know you know this unit, that is Henry for inductance, right? Now L doesn't actually, similar to capacitance, same as capacitance. Okay, as capacitor also, it does not depend on the how much charge is stored on the plates or what is the potential difference. It depends on geometry. Same here as well. Inductance will depend on geometry only. Now how do you find out self-inductance? Okay, I know this particular formula. V induced is equals to minus L di by dt. If I want to write this in terms of inductance, like, what will be the generated EMF due to its own self-inductance? How will I write it? So I know psi is equals to what? Psi is equals to Li. Okay, as psi is equals to Li, this will be equals to, L is a constant, it will not vary with respect to time, so this will be L di dt. Okay, so your V induced, the induced voltage that I was talking about, the magnitude of the induced voltage will be L di dt, and the sign will be negative. Why is the sign negative? It will try to oppose the change. This negative sign actually signifies the opposition in the change. Okay, this formula you already know. Okay, we are studying electrical engineering, so this formula you already know. I know that very well. So this means, this negative sign means oppose the change. Okay, so from this also you can find out units of L. There is another unit of L. What is that unit? Here, if this dt goes on the left hand side and di comes in, right? So it will be volt second per ampere, amp. Okay. So this is also another unit. This is the unit of Henry. Okay. So what will be the direction of induced EMF? Just, I know you know these things. Just if the current is increasing, right, here in the same direction, if the current is increasing, it will oppose. So the induced EMF will be such that it will just oppose the current, right? So it will be from plus to minus. Okay. And if the current is decreasing, in the same direction, if the current is increasing, it will aid the current. So plus will be here and minus will be there. Don't worry about the direction. I will explain all this later on. Don't worry. You don't have to worry about the direction right now. Now, let's derive few expressions for inductance. What is the inductance, self-inductance of a long solenoid? Because I know what a long solenoid, like what is the magnetic field due to long solenoid. What was it? It was at the center. I'm only concerned about the center. It was B was equals to mu ni. If you remember, it was B was equals to mu ni. Okay, and this is the flux. This is the magnetic field, right? Now, what is the flux in a single coil? What is the flux in a single coil? So the flux in a single coil, like this is the coil, right? And what is the area that the flux that the magnetic field will cross? It will be pi small r square, the radius of this. This is the radius of this small coil. So phi is what? Phi is flux due to a single turn. It will be simply magnetic field into area. So phi will be equals to mu ni into pi r square. Okay. Now, what will be the flux due to n turns? Total flux. Because here I am crossing the magnetic field is crossing n number of turns, right? So there will be total psi will be n phi. So it will be simply equals to mu. It was number of turns per unit length, right? So it is not small n, because capital N is number of turns. Here I will just briefly say capital N is number of turns of the coil, and it is equals to small n into L, right? Small n into L. So it will be equals to capital N phi, or what I can replace this? I can replace this with capital N will be equals to N into L, right? Am I missing something here? Am I doing something wrong? Mu ni. This would be the magnetic field. Yeah, that is correct. Mu n capital N is equals to simply. Yeah, that is correct only. I'm trying to identify. Okay, yeah, this is correct only. So it will be n times. It will be. If I replace this n, right? If I replace this n with capital N, what will be it? It will be capital N by L. So this will become n times mu capital N by L I pi r square. So we get this like formula for simple, like what is the inductance? Inductance is flux divided by the current. So I will put this current here, so that will give me inductance. So phi by I will be mu small n square. If you just replace with small n, this will be mu small n square pi r square L, or you can write it at like this, that will be mu capital N square pi r square by L, or in more generalized term it will be mu n square A by L. Okay, so the best practice is you can derive. It will take you seconds, but if you don't want to, you can remember this. Okay, this is the generalized format of inductance. This I will recommend you to remember. This you can remember simply mu n square by A. Just the swapping of the variables. Nothing interesting happening over here. So let's do a question on this particular thing. The total number of turns and cross section area in a solenoid is fixed. So total number of turns capital N and the cross section area A equals to pi r square basically is, these are constant. Okay, next then however its length L is varied by adjusting the separation between windings. So its length is varied by adjusting the separation between the windings. So I can have more space between the windings or less space. So length is varied. Okay, L is variable, but the number of turns and the area is constant. The inductance of the solenoid will be proportional to what? If L is varied, then the inductance, like with respect to L, will like the inductance will be proportional to what? So I can say that like this is the inductance L equals to, I know this formula, mu n square A by simple L, right? So you will say that inductance will be proportional to 1 by L. Okay, and I will say you are wrong. I will say you are wrong or no wrong. You're correct only. Why? Because this was the formula. If you remember this formula, then with the help of this you will say, okay, area is constant, number of turns is fixed, so L will not vary, so L it will be inversely proportional to L, so option D will be correct. But what will happen is, if few students they remember this particular formula, they will tell that okay, area is fixed, number of turns is constant, so it will be directly proportional to L, and this is in option A. But why is this not correct? Because this n, right, this n actually is not total number of turns. This n is what? This n, small n, is basically number of turns per unit length, which is n by capital L. Okay, so here actually L is reducing, L is increasing, and n is fixed, so obviously n will reduce basically. So n actually is a variable here. Okay, n actually is a variable here. So that's why I will recommend you remember this formula, and through this formula you can derive all the other formulas. Okay, so yeah, just don't get confused with that thing. I'll delete this. Okay, so let us derive for a toroid as well. For a toroid, what will be the self inductance? So again, what is the flux magnetic field density due to a toroid? It is mu ni by 2 pi r. If you remember, it was simply mu ni by 2 pi r, simply just whatever it was due to a circular current carrying loop, and or you can replace it with simply mu ni. Okay, why? What is n? N is the number of turns per unit length. Again, what is the length? Length is 2 pi r. Again, I get the same result, mu ni. Again, if I derive this the self inductance, I will get back the same result. So what is flux here? So flux here is basically equals to mu ni, and current is I, so it will simply be mu into n. Okay, it will be even simpler. It will be simply mu into n. But what if? But this is the magnetic field, right? I want to compute the flux. The flux will be what? This magnetic field into area. So what is the area basically here? What area am I covering? This small area, right? Because this toroid has a non-conductive circular ring around it, and which has a radius of small r, right? This has radius of r, so it will cross this whole area. The magnetic field will cross all the area. Okay, so it will be pi r square. So this is only the magnetic field. This will be mu ni times pi small r square. And how many cross sections I have? N cross sections, right? Total n, capital N number of total terms I have. So total number of turns is capital N. So total I will cross n section like that. Okay, so again, if I want to write this small n in terms of capital N, it will be again this, I can convert this into area, and this n can be converted into n by small l. Okay, into a, n square by. So this overall a is what? A is simply pi r square. In this case, L is different. L is 2 pi r actually, 2 pi capital R. Okay, but the formula remains the same, mu n square A by L, whichever I derived previously, right? This will remain same. So this will not same. This will not change. So it's better to remember this. Okay, if you remember this, you will be easily able to identify the self inductance of anything. Okay, so yeah, but do understand this L is the length of this magnetic field basically, and the R is the cross section area about which it is crossing. So it's very important to understand the context of the formula. Okay, so let's solve the basic question. So here in the question they have given, this question came in GATE 2018. A transformer with toroidal core of permeability mu is shown in the figure. So it has a permeability of mu, assuming uniform flux density across the circular core cross section, radius of r very less than smaller, neglecting any leakage flux, the best estimate for mean radius. Now this r, capital R, right, is also known as mean radius, just the average of that outside and inside radius. It is almost equals to capital R. Okay, so these two are almost equals, as small r is very less than capital R. Okay, so I have told this in previous lecture as well about toroid. So we have to identify that. So we have to use the inductance concept here, and with the help of that we have to identify the best estimate for mean radius. So can you tell me what is the inductance of this particular configuration? What is the self inductance of this particular coil? The self inductance of this particular coil will be what? It will be the number of turns, like this this particular thing is generating some current, right? This is generating some current. Okay, so what I can say is, even if you don't remember the formula, what I will do, I will tell you how we can understand this concept. So this is a transformer like thing, and this is an inductor. So if this is the inductor, I know the relationship between the inductor. Okay, what is the relationship? It is VL will be L DIL by dt. Okay, so what is VL? They have told me the voltage across the inductor is V cos omega t. So it is V cos omega t, and this is L. L I know already. The formula for L I know. L into DIL by dt. The derivative of the current. What is the derivative of the current? It is I omega into cos omega t. I omega into cos of omega t. So my L becomes V by omega I. Okay, so what is my L? I know my L for a toroid like this, but do remember what is the self inductance. So this is the L of the primary. Okay, this is the L of the primary. I'm only talking about the L of the primary. Okay, so the primary inductance here basically is this expression, right? And what is the formula for primary inductance? The number of turns which it has. As it is self inductance, I will not take care of this, because after this question we will learn about the concept of mutual inductance. But as I am talking about self inductance, I will only consider the turns on this particular inductor due to its own turns, right? So I have NP number of turns, which I will square NP square into area. What is the area? Area will be pi small r square, right? This is the cross sectional area that it is crossing, so it will be pi small r square divided by the length. Length is 2 pi capital R, right? This is the length that the flux is covering, total flux that is covering, right? So that is the length of the flux. So now what I can do is I can simply replace this thing, right? Just let me check if everything is fine here. Yeah, everything is fine. So if I just replace everything, right, with this formula, I will be able to find out the R. Why did I replace LP? Because I have to find out the R, and I know only one formula for this where R is present. It's the inductance formula, so I will use that. So here NP square pi small r square divided by 2 pi capital R equals to V by omega I. So your capital R equals to NB square pi r square. Okay, pi will get cancelled actually. This pi and this pi will get anyways cancelled, right? So pi won't be here. So it will be NP into r square into omega I divided by V. Okay, and 2 is also there, right? 2, where is 2? 2. Okay, 2 will be at the bottom. Yeah, so V will come here, R will go there, omega I will come here. This will be even, yeah. So NP square R square omega I 2V. NP square R square omega I and 2V. 2V is at the bottom. Only this has the 2V at the bottom. So option D will be right. So these type of questions also sometimes come. So you should know what is like the self-inductance formula. So with the help of self-inductance, you will be able to solve this question. So now let's come to the next concept, that is the mutual inductance. So obviously, if I have a transformer like this thing, right? If I have a transformer like this thing, and if for now it was open circuited, if this is closed, right? If this is closed, there will be some mutual inductance. What does mutual inductance means? Basically, I generated some flux. The flux of this particular coil actually interacts with this, and due to that interaction, it generates a current, and that is known as the mutual inductance. Okay, basically, flux of this is changing something here, the current here, right? So it is mutual. It was previously self because its own flux, with the help of its own flux, I was generating some voltage, but now with the help of some other's flux, I am generating my own voltage. That is known as mutual inductance. So here the same concept they are telling. When the current in one coil primary changes, it causes a change in the magnetic flux through the nearby coil here, right? It causes a change because flux will also flow through this, and that will cause a change here, inducing an EMF in the secondary coil. This process is known as mutual induction, which we have studied in transformer very well. So I will not go too much in depth here because I know you have studied transformer. So I will not go too much in depth here. Just the basic thing is that the flux in the second coil will actually be dependent on the magnetic field produced due to the first coil, right? And it will cut the cross-sectional area here, and that will generate flux in the second coil. And that magnetic field in turn is actually dependent on the current in the coil 1. So current in the coil 1 is changing the flux in the second coil. So that is the main thing. So from here there is a proportionality term comes that phi 2 is equals to M I1. What it is telling that mutual inductance means how much change in current I1 can produce the flux phi 2. That will be given by mutual inductance M. Okay, so this is the definition of mutual inductance. You can understand it through all this. This is basic thing only. And the voltage induced on coil 2 due to change in current in I1 is known as this relationship, that is V induced 2 equals to M minus M d phi di 1 by dt. So just understand this voltage induced in second coil due to a current change in the first coil. So that's how this relation. That's why this is known as mutual inductance, because they are two separate coils. They are not the same coils. Okay, so we can derive for a few basic things. The formula will be same again. Formula will not be much different. Just one difference will be there. So if I have a solenoid inside a solenoid, so two solenoids are there, two concentric solenoids are there. So what will be the mutual inductance? I know. So the outside, I will assume the bigger solenoid, that it is generating some magnetic field. What is the magnetic field? Again, I will take the center formula. B center is what? B center is mu naught or mu ni again. Okay, mu ni. Now what is n this time? Mu n will be capital N2. This has N2 number of turns and this has N1 number of turns. This has N2 number of turns into this is small n, right? This is small n. So this will be total length divided by the total length. What is the total length? It is simply 2 pi r. So I will not write 2 pi r. I will just write here L2. Okay, into I. That is the current in I1 into I1. Okay. Now what is the flux due to this in the second coil? What is the flux to? Okay. So the flux in the second coil. So this is what is the flux in the first coil? This is the magnetic field in the second in the bigger coil. Okay. And two, what is the flux in the first coil? Okay. So the flux in this is not I2. So this is I1. Sorry, this is I2, right? This is current is I2. So I2 is simply here I. So I will replace it with just I. Okay. This is simply equals to I only. So what will be the flux cut? Flux cut will be simply B1 into A, B2 into A1, right? B2 into A1 simply. And there are how many number of turns are there? So each cross section has total N1 number of turns. So I have to multiply this by number of turns N1. I hope you understand the reason. So overall this formula will become N1, N2, mu will be outside, I divided by L2, and obviously area is there. So if the radius is R, then it will be pi R1 whole square. Okay. The difference is formula is this will become area. This will become the area of its own coil. Okay, that's the difference, and the number of turns will not get squared. Both the number of turns will be multiplied. So you can derive this. Okay, and from there you can proceed. So few basic questions I have with mutual inductance. Let's say there are two coaxial solenoids that are made. Now remember, this formula is not that important. Just understand how I derived it. That is important, because GATE does ask question from this. They will ask you some derivation. Okay, they will want you to derive some expression. So we'll see that. Obviously, two coaxial solenoids are made by winding thin insulated wire over a pipe of cross-sectional area A equals to 10 cm square and length equals to 20 cm. If one of the solenoids has 300 turns and the other has 400 turns, their mutual inductance will be. So like two solenoids are one over other, right? It's two coaxial cables. So we can use a simple formula. What have I derived? Mutual inductance M is equals to the number of turns. Either you can derive or you can solve mu N1 N2, and what it is asking, if one of the solenoid has 300 turns and the other has 400 turns, and two coaxial solenoids are made thin insulated wire over a pipe of cross sectional area 10 centimeter cube. So both are cross sectional area 10 centimeter cube, so that doesn't change. So this will be area divided by the length. Okay, length is also I think same for both of them. Yeah, just the number of turns are different, right? Yeah, and length is also same for both of them, 20. So this will be simply equals to, this is mu, nothing is mentioned, I will assume mu naught into n1 into, so this is just a formula based question. Sometimes formula based question also comes. So this will be 300 into 400 into area will be 10 raised to power 10 into 10 raised to power minus 4 divided by 20 centimeter, 10 into 20 into 10 raised to power minus 2. So this will come out to be how many zeros I have? 1 2 3 4. This gets cancelled. This is 1, this is 3, this is 1 again, this is 2, 10 raised to power minus 5, 10 raised to power minus 5 is there, and this 2 10 raised to, I will write this first, 10 raised to power minus 5, this 4 and 4 16 into 8 into 3 24. So this will be 2.4 something like that, right? Yeah, another 0 will come, so it will make it 10 raised to power minus 4. So 2.4 pi. Okay, so option D will be correct in this case. Okay, so here just simple computation, just formula based, that's why I'm not explaining here, just use the formula, that's it. Okay, for these type of question use the formula, but gate won't ask this type of question, but just I want you to have a bit of practice, that's why I'm solving these questions. Okay, now one interesting question there is the next question. I want you to try, please pause the video and try to derive the expression for the mutual inductance of the following figure. Okay, if what will be the mutual inductance for the following figure? Can you derive the expression? So for these type of cases you have to solve using basics. So what was the definition of mutual inductance? It was the flux due to the coil 1. Okay, flux due to the coil 1 not flux in the coil 2, sorry, flux in the coil 2 divided by the change in the current or current generated in the coil 1. Okay, so this was the definition of mutual inductance. So what is the flux basically? I cannot directly explicitly say what is the flux here, because here flux is changing. Why? Because if I just take this figure, magnetic field is not uniform here, right? What is the magnetic field? Magnetic field, let us assume this is some distance x. Okay, so what will be the magnetic field at this x? Magnetic field B1 will be simply mu, nothing is mentioned, so I will assume mu naught only, mu naught I upon 2 pi x. Okay, so it is not uniform. So if it is not uniform, obviously it will keep on varying. So what I can say here is that as it is a function, so I can take a small cross section like this of very small length dx, and its length is b, that is fixed, its length is b, right? This is a square of bb side. So I can take a very small cross section area of dA, its length is dx and its height is b, so the area will be b dx, and in this small cross section I can identify the flux. Small flux will be b of x into dA, correct, which is equals to whatever this is, this value I will just replace here, and to calculate the total flux from 0 to phi throughout this whole surface d phi, what I need to do, I just need to do the surface integration, right? So I will do bx is what, mu naught I divided by 2 pi x dx, and obviously b is also there, right? B is also there. X will go from what? X is here at the edge of the left hand side, it is a, and here x is equals to what? A plus b. X is equals to a plus b. So my phi, this is phi 2, flux on the second coil. Phi 2 will be equals to, this is I1, right? This is just I1 is the I itself. So it will be phi 2 will be simply this is ln x, right? Mu naught I upon 2 pi b is there, ln a plus b divided by a. So it will become, if I divide this by 1, right, it will be 1. So what will be my inductance basically? So if I replace this, right, if I just take this I on the left hand side, so my m will be phi 2 by I, which is equals to mu naught b divided by 2 pi ln 1 plus b by a. Okay, so it will be simply ln 1 plus b by a. So option C will be correct. Option C will be correct. Okay? Option C, yeah, option C is correct. So now I wanted to do this question. Okay, this question came in gate 2020. So very recently this question came up. So you must do this question. Okay, so same concept, exact ditto same concept has been asked. Just here they have put the values. So in examination hall, will you remember this formula? Don't. I am telling you in bold words, don't remember. Okay, they want you to derive, because one day they have asked this concept, right? Next day it will be something circular. How will you solve? So they will change everything, right? They will make it rectangular. Okay, please don't remember this. Just derive. So the solving methodology will be same as the previous question. Because I have already arrived to a result, I will directly use the formula here. Okay, but what you will do in the examination hall, you will derive the formula, then we will put the values. Okay, so just step 1, derive, and then step 2, you will arrive at the formula. What will the formula? Or you can directly put the values as well. X equals to 1 to x equals to 2. That's it. So then you will put the values of the formula. So put values. So your m is equals to mu naught I, mu naught this width of a distance, mu naught a by 2 pi ln a plus d divided by d. So this will be 1 plus a by d simply. Yes. So d divided by a plus d. Yeah. So this will be equals to, like, I will directly write here all the things. So I they have given me, but I even need I? I don't even need I. Okay. So they have just given the I for the sake of it, because you don't need it. It will be independent of I, right? So this will be 2 into 10 raised to power minus 7, because they have not mentioned what is the medium. So I will assume it as vacuum into A. A is 1 meter. 1 meter into ln of 2 simply. 1 plus 1 is 2. So what will be this equals to? So this, if I just solve this, 2 ln into 2, this will be 1.36. And if I just take more, if I multiply this with 100, this will be 138. They have asked us in nano Henry. So please do take care of the units as well. Nano Henry. So I will convert this into nano Henry. This will be 138.63 nano Henry. Okay, this will be your answer. So ditto same question can get asked in examination. Okay, but with a bit of twist. So I will recommend definitely with some, like, you do the derivation. You don't directly remember the formula. So then there comes the inductor. Okay, inductor is basically what capacitor, right? It's the same thing. It's just inductor is simply a solenoid, which we have been studying. So just few terms we need to study. That's it. So what does inductor do? It creates magnetic field. And why is it very important? Your whole universe works on this, right? You see the transformers. Okay, you are getting the electricity. How you are getting the electricity? With the help of transformers and water transformers. Basically, it's 2 inductors are there. Basically, that's it. That's the basic thing. Okay, so few things are there, like self-induced EMF and all those things. Inductor opposes changing current. Now, as you are already electrical engineer, I'll not go too much into all this, right? You can go through the slides and you already know about this. As you are electrical engineer, I don't think it's my duty to tell you all this, because this we already studied in the like our first year. Okay, so like it opposes the change in current, all those things you have studied in networks, so I will not go through too much, just how the direction of EMF will be, all those things. It will oppose the change. Okay, whatever, if the current is increasing, it will try to reduce it by creating a induced EMF L di by dt. If the current is reducing, it will try to increase it, it will aid the current. Okay, all these things you know. So another is work done by a battery. So like what we can do understand is how to find out the energy stored in an inductor. I will just derive the expression. Okay, so if I have a RC circuit like this, then once I close the switch at steady state, whatever energy this battery has dissipated, right, some of it will be stored in this inductor and some of it will be dissipated as the form of heat by this resistor. That is what is written. This is at steady state. What I want to do, I want to derive the energy stored in an inductor. So at steady state, this will happen. So can I derive it? So what will be the small work done by a battery? What is the small work done by a battery? The definition of work done, if you remember, it was Q times dV, change in potential. Okay, these things are interchangeable. So it is Q times dV, right? Change in potential. Okay, so not Q times dV, sorry. V is the potential difference and the change in current. Small change in charge, that because few charges have been went out of the battery, so the amount of change in charge into the potential difference will give me the work done. Okay, now this I can write in some different manners as well. So what is dq? I know dq will be simply equals to I dt, right? Because dq dt is I, so I can replace this thing here. So basically my dwb is replaced with I vi dt, correct? And what is the energy, thermal energy in resistors? I already know the energy stored in inductor, but I just want to derive the formula. What is the small change in thermal resistance, right? Like thermal heat? So it is dH equals what? It is I square R dt, small change in time, right? I square R dt. This I square R will be constant, just small change in time. This is the amount of heat dissipated, correct, through the resistor. So I know by KVL, V will be equals to VL plus V R, right? So what I can write is this V is equals to L dit by dt plus I into R. So if I multiply I dt on both sides, what will I get? This will be Vi dt equals to L I di plus I square R dt. So this is basically the dH. This is the work done by the battery, and this must be the energy stored in the inductor. Okay, so what I can say is, if I integrate on both sides now, with respect to like I, so like this must be energy stored by inductor, small energy stored in the inductor, right? So dWL will be L di. This must be the small energy stored in the inductor, right? So now if I integrate, what will be the total energy stored in the inductor with respect to I? If I is going from 0 to I, steady state, L I di, so I'll get my formula for energy stored in an inductor, that is half Li square, which we already knew, just wanted to prove in a different manner. If you didn't know this proof, then you now you know, congratulations. So this will be half Li square, that's it. Okay, now there is another term known as energy density. So what will be the energy density? Basically total energy stored in the magnetic field divided by the volume. So I have derived it is equals to half Li square. So what is L equals to? L for a solenoid, L is mu into n square A divided by L into I square. This is the L, right? So here I can write in different format as well. This will be half mu n A into L. What is this n? N is the number of turns per unit length as derived previously into I square. This is my UL. So what is A into L? A into L is simply volume. So my small u will be half mu n I whole square. Now one small thing I can do is B is mu n, right? B is mu n. Okay. So if I just get this, actually, sorry, this will be n square, at mu n square, this will be n square. If I just multiply and divide by mu, I will get it as a generalized expression as B. So I will multiply and divide by mu. So this will become half B square by mu. Okay. If you remember, this is almost same as the electric field. Electric field also had a similar relationship. So that is what it is written over here. So your magnetic field potential energy per unit density, like its per unit volume, will be half magnitude of B square by U, or you can replace this magnitude of B in terms of magnetic field intensity. It will become then half mu H square, or you can write in terms of vector as well. It will be the dot product of two. So like, are you able to recall anything? So for electrostat, we had something like this, right? It was half D dot E, or it was equals to half epsilon magnitude of 4 by epsilon. So if I multiply both on epsilon, so it will be magnitude of E square. Okay, or it is half magnitude of D by epsilon. Okay, either one of them works. So just same thing here, energy is potential density. So this is always valid. Remember, this thing is only valid for a small volume. So if I choose a small volume and the magnetic field is as such, so always remember, always valid for a small volume, not for very large volume, right? Always valid for a small volume. And if the magnetic field is constant, then also it is valid. Okay, so this was just a few formulas, so they can ask questions from here, and that's why I have to tell all this. Just I'm also trying to recall the previous things as well, which we already learned. Okay, now there is like combination of capacitors were there, combination of inductors also there, but this is not that difficult. It is just simple. Okay, bacha thing. So what is it? L equivalent, we already know it is L1 plus L2 if they're in series. If they're in parallel, we don't talk about any mutual inductance. If they're in series, we talk about mutual inductance. If they're in parallel, the simple equation which you already know, it is L1 L2 divided by L1 plus L2, L equivalent. Okay, so if they're in series, right, sometimes we can place this coil such a way that both of these will oppose each other. Okay, and the M is what? M is basically the mutual inductance. Okay, when both of them oppose each other, basically the flux due to this opposes the other flux, I will say L equivalent will be minus of 2M. When both the flux aid each other, if both the flux aid each other, then I will say it will be plus 2M. So how do I understand that? Here let's take this case, right? Here current in both the coils is in same direction. If the current in both the coils is in the same direction, I can say both of them are aiding each other. How can you say both of them are aiding each other? So this is the coil. I will zoom in here, right? I will zoom in. So actually the coil is this zoomed in, okay? Zoomed in thing. So current is flowing like this in the clockwise direction. Now if I curl my fingers, for L1, magnetic field is on the left hand side. Okay, curl my fingers, magnetic field is on the left hand side. Same if I zoom in this L2. Okay, I will just use some other color. Again, the current is in the same direction, right? It is again like this. So it is placed like the coils are placed like this. So again, if I curl my fingers, the magnetic field is again in the left hand side. So both the inductors actually additive, both are acting in the same nature. That's why the mutual inductance also gets added. M plus M becomes 2M. So mutual inductance get added, and the formula for mutual inductance is this: M equals to K under root L1 L2. That's just a constant thing. That's a formula thing. Okay, there is nothing to derive here. Yeah, sorry for the interruption. I just pushed the phone and it just dropped. So what I was telling, if they are in same, right, they will be additive. So this will be L equivalent will be L1 plus L2 plus 2m. Now if the coils are oriented in a different manner, so what do you mean by different manner? So here the current is like clockwise fashion, right? But here the current actually is in the opposite fashion. Okay, it's in the opposite fashion. So this is telling me, if I just curl my fingers, this is telling me in the magnetic field generated by this is on the right hand side, and the magnetic field generated by this is on the left hand side. So both are actually opposing each other. That's why there is a minus sign. That's it. Both are opposing. That's why there is a minus sign. Okay. So if they are oriented in same fashion, in same sense, they will be additive. If they are oriented in opposite sense, they will be subtractive. Okay. So a few basic questions are there. Let's do this. So two identical solenoidal coils, each with self inductance L, are connected in series. The coils are aligned so that their turns are in same direction. So whenever there is same direction, that means they will be additive. So basically our L equivalent will be L1 plus L2 plus 2m. Okay. The distance between them is such that coefficient of coupling is half. So that this k term, right? This k term is the coefficient of coupling, or also known as sometimes like coupling coefficient. For tight or perfectly coupled, k is 1. Otherwise, it is always less than 1. Okay, and the formula is k into under root L1 by L1 into L2. Okay. So coefficient of coupling is half. So m equals to half into under root L1 L2. Both are of L. So it will be under root L square. So it will be L by 2. So here basically it will be L plus 2 into L by 2. So it will be 3L. So answer will be simply C. Okay. So what is the equivalent inductance of the combination? So it will be 3L. Just bacha type question. Okay. This also is a bacha type question. The question is same, but here they are in opposite direction. If they are in opposite direction, L equivalent will be L1 plus L2 minus 2m. So m is L by 2. I have derived in the previous question. So it will be L plus L minus L. So it will be simply L. So option A will be correct in this case, right? So these are all bacha type questions, and I am not putting more emphasis because I think you already know all these things. Okay, these are basic things only. So yeah, that's it basically for this lecture, and that's it for the electromagnetic fields. I hope you have enjoyed the whole series, the whole subject. If you have come till this end, right, I can assure you that I can guarantee you at least I cannot say that you will be able to score 100% in this subject, but what I can say is you will be able to understand the question. Whatever the question is asking, everything you will be able to understand if you have studied the lecture diligently. Okay, everything you have studied diligently, you will be able to follow through. So I have tried to concise everything in the shortest way possible, but not reducing the quality. I have tried to maintain the quality to the highest level, and trust me, like you can, if someone has already studied electromagnetic fields previously, they will understand the difference. How am I teaching and how they are teaching? So yeah, you can put down below in the comments if you have finished till this end, and you can put your reviews and all those things about the content and quality, all those things. So yeah, that's it for today's lecture. All the best for your examination, and I hope to see you in the next subject. Until then, happy learning.